All right, our next presentation this afternoon is from Riya Shrivastava, who joins us from Caltech, where she'll be a sophomore this coming fall. Riya's been working this summer with Kyle, and she'll tell us today about her project studying electromagnetic transients from stellar collisions in young star clusters. Go ahead whenever you're ready.
Thank you so much for the introduction, Gwen, and I'm really excited to present the work I've been doing this past summer. So beginning with a brief introduction, what are star clusters? So kind of the two main ones that might come to mind are globular clusters and young clusters. So globular clusters are older star clusters. They're much more massive and have a much greater number of stars and are much more compact. But in contrast, our work is kind of focusing on young star clusters, which, as the name implies, are pretty young. So maybe tens to hundreds of millions of years old. They're less massive and they kind of have a more loose open formation. However, these clusters, regardless of age, can still kind of vary in their density. So one of the challenges in computational astrophysics in the past has been modeling these dense star clusters. But my mentor has been working on some cluster Monte Carlo code that contains all the relevant dynamical information for accounting for scatterings between stars or strong encounters. This could be collisions or mergers and whatnot. And it also prescribes to kind of the latest field studies of single and binary stellar evolution. So using this code, we're able to create n-body models of our clusters that kind of show how these young clusters evolve. Because of the high densities in these star cluster cores, they're able to facilitate a large number of dynamical interactions, which lead to many, many stellar collisions, especially within the first few millions of years of these star clusters. And especially for massive stars, these collisions can lead to unique stellar evolution pathways. So one such example is a pulsational or a pair instability supernovae. And these are formed when stars with helium cores of 45 to 100 solar masses undergo the electron-positron pair production at the onset of carbon burning. And this leads to a rapid loss of pressure and core contraction that triggers an explosive burning of heavier elements. If a star's core isn't within the range 45 to 65 solar masses, this process leads to a damping pulsation. And these are also pretty interesting because they have implications upon the mass spectrum of black holes. Specifically, they lead to a prominent gap in the black hole mass spectrum. However, recent studies have shown that massive star collisions that occur within the first few millions of years of a young star cluster can actually lead to the formation of massive stars that circumvent this pair instability process and subsequent explosion, which could actually lead to the formation of black holes within the proposed upper mass gap. Another thing that we can form are intermediate mass black holes, which are kind of in between stellar black holes and then the supermassive black holes in the center of galaxies. So they have a really wide mass range. And LIGO and Virgo have recently detected a 142 solar mass black hole merger, which is kind of the first detection of an intermediate mass black hole, but it's unclear if this black hole was formed in a cluster. So this is kind of a plot that explains everything I just talked about on the last slide. Looking at the plot, you can see that the final core mass is what ultimately affects what kind of transient or black hole is formed at the time of collapse. So here there's a big gap within the pair instability range where the star is destroyed. And otherwise, this black line is kind of tracking the mass of the black holes that are able to form with these final core masses in mind, whether it's within the supernova range or it directly collapses into an intermediate mass black hole. So for our project, we looked at 40 n-body cluster models total. These models had a fixed total mass, and they also had a fixed massive star binary fraction. So all massive stars greater than 15 solar masses were in binaries, which is pretty comparable with observations in the local universe, which have shown that most massive stars are in binaries. We also had 10% of all stars in binaries, so, or the less massive stars in binaries, which is kind of a parameter you can vary. And the two things that we varied within these 4D models were virial radius and metallicity. So we varied the density of the stars, and we also varied the metallicity of the clusters. And our goal was to identify various black holes and transients that were formed. So collision histories and results. This slide kind of shows a sample of what a collision sequence for a pair instability supernova or an intermediate mass black hole could look like. And this way we can kind of see how they're able to accumulate more massive cores over time. So for the pair instability supernova, we can see that collisions 1 and 2 are kind of the collisions of interest, with 2 fairly massive stars colliding. Whereas for the intermediate mass black hole, collision number 4 has a 3-star collision, which could be a binary and another star. And that leads to the accumulation of a large core mass. And all the way at the bottom, the kind of highlighted yellow numbers are the, it's the core mass of the star at the time that ultimately allows it to collapse into either the supernova or the black hole. So for our results, we kind of wanted to compare how the different parameters of our model would affect the number of black holes or supernovae that would form. So looking at this plot, we can kind of see that across all models, they have a similar number of total black holes formed. And especially from the range 0 to about 45, there's kind of an equal number of black holes that are formed. But after that, within the mass gap black hole range and the intermediate mass black hole range, there's much more variation. So we can see that the blue histogram, which represents the model that had 10% solar metallicity and a virial radius of 1, is able to produce significantly more of these kinds of black holes. And kind of the model that produces the least black holes is the model that has a metallicity that is 100% of solar metallicity and a virial radius of 2, so a less dense cluster. And we also tracked the number of pair instability supernovae and pulsational pair instability supernovae that formed. So the numbers on the plots are kind of the average number of these transients that formed across our 10 models. So we had 10 models and we kind of averaged the numbers. So again, we can see that the blue model is the most successful in producing the largest number of these transients. And this actually makes a lot of sense because having a lower metallicity model means that there's less mass loss due to stellar winds, which allows for more massive stars to collide and the accumulation of a greater core mass. And additionally, having a smaller virial radius, so 1 parsec as opposed to 2, means that there's a greater stellar density, so it allows for more of these kind of dynamical collisions to occur. And then we also just wanted to track the number of collisions formed from black holes or mergers, similar to kind of the LIGO detection earlier. So we can see again that it's the model that has 10% of solar metallicity and the smallest virial radius was consistently able to produce kind of most of these. One thing to note is that the number of mergers is pretty similar across a couple of the models, and this makes sense because the number of mergers is largely dependent upon the initial binary conditions, which we had kept consistent throughout the various models. But otherwise, collisions are just pretty much primarily affected by the stellar density of the model. We also wanted to calculate some rates to compare our results to current observed transient rates. So using this equation, we found that the rate of pair instability supernovae within our models was 0.21, and the rate of collapsars, which are black holes formed from collisions or mergers, was 65.1. And our rate of collapsars is pretty comparable to the long gamma ray burst rate of about 100. So we can kind of see that our results are pretty comparable, but our results for the pair instability supernova rate is significantly less than the average core collapse supernova rate. of 2.5 times 10 to the fifth, which kind of maybe explains why we have not yet been able to observe these transients. But there is hope that current and upcoming transient observatories, for example, Vera-Rubin Observatory, could potentially observe these very bright events. So we found our rates for the pair instability supernovae and our collapsar rates. We also found that roughly 10 to 15% of all black holes in clusters are formed from previous stellar collisions and mergers. And this is interesting because if these black holes are able to retain their angular momentum and form mergers with other black holes, this has important implications for future gravitational wave detections by LIGO and Virgo. And we also can observe that transients such as pair instability supernovae and long gamma ray bursts can potentially yield unique elemental abundances in which the host cluster can be enriched by this material and kind of hint at the occurrence of these events during early stages of the cluster's life, kind of showing that they do actually occur. And something and something to kind of look forward to is intermediate mass black holes, which again have been speculated to exist in clusters, but there have not yet been any confirmed detections. But they could be detectable by future low frequency gravitational wave detectors like LISA, so that's kind of exciting. Looking at the plot, you can see that LISA kind of observes these objects at lower frequencies and could be able to potentially find these more massive objects within clusters. And that's all I have for my presentation. Thank you so much for listening, and I want to thank my mentor, Paul Kremer, for being super helpful throughout this whole process, and I really enjoyed working with you. And I'm happy to answer any questions. Thank you.
All right, nice job, Riya. Do we have questions for her? Ilva.
Hi, thank you so much, Riya. It was really interesting to listen. I wanted to ask, because I could see that you created some black holes in the second mass gap. And I was curious, how did you create those black holes? Do they come from black hole mergers, or is that a product of a star that has merged with some other kinds of stars and then collapsed into a black hole?
Oh yeah, so I think we found that the kind of thing that I had mentioned earlier was that there was some studies that had shown that collisions that occur really early on within a star cluster's formation kind of are able to circumvent the pair instability process. So if they kind of have a core mass within this range here, but it occurs very early on, they could potentially still lead to the formation of a mass gap black hole. And in terms of if it's from a collision or merger, I'm actually not quite sure, but I would imagine that definitely many collisions would kind of be involved in building a core mass large enough for that to occur.
Right, that sounds to me like, because the scenarios that I am familiar with, that where you may be able to create something in the pair instability gap, could be if you have a really small core in comparison to the envelope, and all of that collapses to a black hole. So I was just curious whether something like that was implemented, or whether it's partially also from a merger with a black hole, or maybe some exotic merger with a star and the black hole. Like that would be fun.
Yeah, I think in this case it's definitely the latter. So maybe more from a merger or collision as opposed to just something with a really large envelope and a small core. At least for kind of the way we analyze these models.
Okay, interesting. Thank you.
Thanks.
Awesome. Other questions for Riya? So I was curious about the rates that you calculated. So when you went through and did that calculation, I was wondering what you were assuming for, oh wait, actually it's on the slide, the fraction of the stars that form in stellar clusters. So basically you're assuming that 1% of all the stars form in the stellar clusters, and that they all have basically the metallicity and density distribution that you're in a particular model. Is that right?
Yeah, I think we kind of picked that because it was kind of an average rate, or I actually believe that my mentor had worked with a previous student who had kind of calculated this rate for some similar models, which is why we used it, because the upper bound would just kind of be that all the stars are formed in the cluster, which is maybe not as realistic.
Perfect. All right, thank you so much. All right, I think we will move on, but let's thank Riya again for her presentation.
Yeah.